that you need to do. And you can only limit yourself to an offline assessment of the performance of the PMUs this way, because doing it manually, I mean, there is no way you could actually use that data to make some decisions in real time, so to say. So therefore, I switched to OpenPTC in the middle of the project, and it allows a higher degree of interaction. And I also developed a MATLAB library to automatically import data from OpenPDC into MATLAB. And why? Because already I had the functions in MATLAB. I could have implemented something in C#. OpenPDC is written in C#. But since I had all the algorithms in MATLAB, why bother? Because the time was short anyways. And the thing is, it interacts with a continuously running web service, this MATLAB library I have developed. And through this web service, OpenPDC is able to give me whatever I request from him when I requested. So just to have an idea here, this is a schematic. So OpenPDC has this web service, and I submit interrogations to its database, to its archiving. Everything is optimally stored and archived here. It's not my problem. And I submit an URL query, and I get an XML file. And I parse this XML file, and I export the reply into MATLAB files. So from here on, I have all the MATLAB power at my disposal. So also the SIG ACQ library at work. You see here I have OpenPDC extract, and I specify the name of the test, the date when the test was performed, and the duration, and I get all this intermediate output, and then I get the answer here. So it's that easy, and this answer actually gets exported into this mod file over here. You can see here the root of the library. Now the most interesting part is obviously post-processing. So there were like two indicators. The main indicator for the tests in the standard was the TVE, and for more complex signals like the ones simulated in Dixieland, we identified the frequency and damping factor electromechanical oscillations, and we compared it with Dixieland's embedded model analysis. That was the main indicator. So we even developed the Cigana library, which automated the post-processing and analysis of the test set. For example, it came in really handy because we had a problem, as you can see now, with the steady state tests. I mean, with basically all the standard tests, all the tests defined in the standard, because we kept getting a phase shift between the simulated values and the acquired values of somewhere between -7.5 to -9.5 degrees. Now the amplitude was okay, so I mean, of course we investigated this problem thoroughly, and it took us a lot of time until we realized it. But I mean, the phase shift can be translated into a synchronization error of 0.47 milliseconds, which is a lot. I mean, we had the Omicron starting the test at exactly so to say. Okay, sorry for this interruption. I had to gather my thoughts for a second. At the transition at the pulse of the GPS, so we should have started the cosinusoid at exactly the time when the PMU reference was at 0. So the PMU should have measured 0, but instead it measured like -8, -7.5, -9 point something. So in order to be able to detect this, I actually made a function that analyzed all the tests and nicely output. For example, we have for only voltage, 16 tests, and for all phases and for all PMUs. This is the difference between what we got and what we expected to get. So as you can see, they are all in the range of -8 point something, -9, -7 point something. So something in the synchronization system, which you can see here, wasn't doing its job. It could have been the rooftop antenna number 2. It could have been cell 2401, which was providing IRIG-B for the PMUs, or it could have been MICOM P594, which was providing 1 PPS signal for the PMUs. It could have been the small GPS antenna here of the Omicron. It would have been the CM-GPS converter, and actually in the end it proved to be the CM-GPS converter. And on the producer's website we found out that they do not recommend using this. I mean, it was a document posted something like 2 weeks or 1 week and a half before the deadline when we had to finish our work. So it was a recent document when they said, okay, don't use this, it inserts delays, it inserts phase shifts. Use instead CM IRIG-B, which is way better, and this is the only tool we recommend for accurate synchronization. So there was nothing that we could do at that point. Ordering a new equipment wasn't worth it. We wouldn't have had the time and the money anyways. So we had to deal with these phase shift errors and we had to correct them. So we applied a rough correction based on the output phase shift, so to say. We took the median value, and the PMU TV response remained qualitatively the same, but of course the values are not. I mean, if we said it is 0.9%, I mean 0.9% means nothing. 0. I mean, the PMU, for example, you will see later on, the TV will spike whenever we have a transient and then come back, and then the time to recover is qualitatively the same, but the values in between, I mean, you cannot say accurately because the TV takes into account the phase shift error, and we don't know if the phase shift error is the one that we have corrected, obviously. However, no corrections were applied for estimation of interior oscillation just because you have an input signal, you get an output signal, and you're only interested on the waveform. You're not interested in if that waveform is a little bit to the right, a little bit to the left, if it is a little bit delayed. So this is the advantage of estimating these qualitative parameters of the input and output waveform. So this 100% holds. And as you will see later, we had actually good results with this. So this is a scheme of the correction. So we have the simulation, we keep the amplitudes, however, we have to correct the angles with the median approximations, and then we get the final results by making this comparison here. Here are some actual results. So these tests in the left were made for extremely low amplitudes, and we can see we have a higher TV compared, for example, to the T10. I think it's T10 is the nominal. It was a test performed at the nominal amplitude, and the same thing for PMU2. Also, you get a TV variation during the 10% voltage amplitude step tests. You can see how the TV raises and then drops down till the PMU window goes over this transition. You have exactly the same variation in case of a phase angle. Phase shift, as you can see, the variation is much higher. It's in the order of, I don't know, 80%, something like that, which is huge. So you can observe a much higher sensitivity in case of an angle shift. Also, this is a test where the PMU kept up with the frequency ramp so the multiple frequency step up tests. However, if we apply instead of 0.5 hertz, if we apply 5 hertz, which is the next so to say, the next, there are two tests defined in the standard. One where you apply a 0.5 hertz step, and the PMU has to keep up with the frequency estimation. And one where this is called level 0, and level 1 where it's more strict, you have to apply a 5 hertz test. I mean, the PMU doesn't cope up with the 5 hertz step, but it does cope up with the 0.5 step. Okay, and estimation of interior oscillations, we used a windowing technique. We prone with a windowing technique. As you can see, at the beginning of the tests and at the end of the test, considering the fact that prone is very sensitive to noise, we get all these unusable estimations, so to say. So that's why whenever we use prone to estimate anything, we take exactly the median values, because this is the signal is the cleanest, so to say. And we have generated with VOSC, if you remember the equations described for the VOSC function, we have generated a 2 Hz and 0 damping sinusoid, and prone has estimated 1.99 and minus 0.01, which is great. It's 1% accuracy. Then we thought, okay, we are ready to use our prone method on the Dixieland extracted signals. So these are, for example, 2 signals at the 2 buses delimiting the tie line, and we have applied prone on the angle difference, and we have compared it with Dixieland embedded model analysis, as I have mentioned previously. And this is, for example, to get an idea what kind of interior oscillations we are to expect, is around 0.55 Hertz and 0.11 damping factor, and prone is doing again a good job in estimating this. And these are all the tests that we have performed, 6 tests in general. And as you can see, the right side load has been varied, has been decreased, and this has affected the frequency and damping on both, obviously on both model analysis and prone on output signal. And if you compare, this was a bad test. If you compare all these tests, if you compare the frequency here with the frequency there, frequency here with the frequency there, damping here with the damping there, you will see that you have 2 digits precision. So the results are relatively accurate. So the conclusions, we have automated both the test generation, data acquisition, and analysis process in order to be able to achieve online estimation of interior oscillation. Also, the 2-digit precision of the prone algorithm, which we have tested both with Dixieland and both with mathematically modeled electromechanical oscillations, proved that what our estimation was reliable. And in the end, we have achieved a versatile testing platform capable to qualitatively assess WAM's performance. I mean, despite all the phase shift errors introduced by the measurement equipment. So I hope you guys liked it. I won't be able to answer any questions, or maybe I will if you leave them in the comments down below. And thanks for your attention. Have a nice night.